In the last video, we proved that because the laws of physics are invariant throughout space, the same everywhere in the universe, momentum is in general conserved. That's quite a profound result. As you might be able to glean from this title, we're going to do the same thing here, but for energy conservation, which is tied to the time invariance of the laws of physics. Just a little word of warning, this is going to be slightly more abstract than perhaps you've been used to so far, but it's also going to be useful for a few things that we do later, so I'm going to go through with this exercise regardless. So consider now a Lagrangian, which depends on a set of generalized coordinates, q1 through qn, and the corresponding velocities, of course, and also time. So this could describe any of the systems that we have worked on so far. I'm not going to take the time derivative of this, the full time derivative. And to do this now, I'm going to be applying the chain rule. Because the meaning of q sub I dot is the full time derivative of q sub I. Okay, just a chain rule. That's all we did. Now we're going to apply the Lagrange equations. Like that. So we take this derivative is actually equal to the time derivative of the generalized momentum that corresponds to this generalized coordinate. So that gives us a way of replacing this, right? You can see that this is just equal to p sub I dot, and this of course is equal to p sub I. So we therefore have all right. Now we're going to assume here that we're working with a Lagrangian that doesn't actually depend explicitly on time. So this time dependence is going to go away. So that means that the partial derivative of the Lagrangian with respect to time is 0. That doesn't mean, of course, that the Lagrangian doesn't change over time, but it does so because the generalized coordinates and the corresponding velocities change over time. Okay, and this is a property of the laws of physics as well. Right? The laws of physics do not change over time. So if we have an isolated system, so that there's no time-dependent influence from the outside, then the laws of physics, which are working there, which are working on the internal mechanics of the system, they don't change over time, and therefore there's no explicit time dependence of the Lagrangian. By the way, when the Lagrangian doesn't depend explicitly on time, we say that we have natural coordinates. So this means, for instance, we don't have any forced constraints that vary with time. You've seen in some of the problems we've solved up to now that if we impose a force constraint, like a forced rotation, for instance, then the Lagrangian is likely to have explicit time dependence. And that's not the case we're considering now. If that is not the case, then we say that we have natural coordinates. Just some lingo. But since the laws of but the main take-home point here is that because the laws of physics are time invariant, then the Lagrangian for an isolated system must be explicitly time independent. In other words, it doesn't depend explicitly on time. So that means that we can get rid of this term. Okay, so with that now, we can say that we can take a look at this, and we can see that really what we have here is something that looks like a time derivative in and of itself. So this just looks like a time derivative of plus that in principle, but we're going to say that that's 0. Okay, now we're going to construct a new quantity, which we're going to call the Hamiltonian. H. The Hamiltonian is equal to the sum of P sub I, Q sub I dot, minus the Lagrangian. Okay, now we just showed that the time derivative of the Lagrangian is equal to this. So with this result here, we have that if you take the time derivative of the Lagrangian, of the Hamiltonian, excuse me, well, it's going to be equal to the time derivative but the time derivative of the Lagrangian is this. So that's equal to 0. In other words, if we have natural coordinates, that means that the Hamiltonian is conserved. Okay. So if we're dealing with an isolated system, the Hamiltonian for an isolated system must be conserved. So the only question is now, what's the physical interpretation of the Hamiltonian? Well, what I'm going to show next is that the physical interpretation of the Hamiltonian is that of energy, provided that we're working with natural coordinates, but we already said that we did. And that means, of course, that the time invariance of the laws of physics means that energy is conserved. But let's not get ahead of ourselves. Now let's construct here. Let's see here that this is what we want to prove. We can call this a theorem if we like. So if the generalized coordinates don't depend explicitly on time, then the Hamiltonian is the total energy of the system. All right, so let's prove this. So with natural coordinates, that's what that means. The generalized coordinates don't depend on time. We have that all the Cartesian coordinates depend only on the natural coordinates, not explicitly on time at all. So this means if we want to then calculate the velocities, okay, that's what we get just taking the time derivative of the Cartesian positions of all the particles. Now, working with Cartesian coordinates means that it's easy to write down the kinetic energy. Kinetic energy is just, 1/2 mv squared. But we have multiple particles here, so we have to sum up the mv squared term of all the particles. But then we just derive this relationship, so we can just plug that in here. So now we get a triple sum. Hope you're with me so far. All I've done here is I've calculated the kinetic energy. It's 1/2 of the mass times the velocity times the velocity. But I've shown I can write the velocity just using the chain rule as in this fashion with respect to the generalized coordinates. So this is just a general way of writing the kinetic energy in terms of the generalized coordinates. And I'm just going to rewrite this on this form. Right, so all I did is I took some of these derivatives and the masses and the sum over alpha and just plucked it all into this matrix here, so that the matrix element a sub ij is just equal to this. And these derivatives are vectors here, so there's a scalar product between them. Okay, so that's just a shorter way of writing this mess here. I'll put in these parentheses to make it maybe slightly clearer. Okay. Now we know then that the generalized momenta is this. And the generalized momenta depend only on the kinetic energy because the potential energy in general does not depend on the velocities. It would not be a conservative, would not correspond to conservative force in that case, and we wouldn't have the second law, the second condition for conservative forces be valid. So this is always true. And note here that this matrix is perfectly symmetric, so I can change the order of things of the indexes any way I like. And it doesn't depend on the velocities. A sub ij does not depend on the velocities. So the only thing that happens when I take the derivative with respect to the velocities here is that I have to consider these terms. A does not depend on them. So we now have an expression for p sub I, the momentum. And now we're going to construct this sum here that we saw earlier. Okay, that's what we get when we do that. Oh, and by the way, there was a 1/2 here that disappeared. It disappeared when we took this derivative here, right? Because there are two terms in this sum. They contain the ith term in principle. So that's why when we take this derivative, this half disappears. So now when we look at this, we can see that that's actually exactly equal to twice the kinetic energy. Right? So if we now write down the Hamiltonian, let's remind ourselves what the Hamiltonian was. We had defined in this way. That's the Hamiltonian. Okay, we just show that this term here is twice the kinetic energy. So that's 2t minus the Hamiltonian, which is t minus u. So that's 2t minus t plus u. So that's t plus u, or the total energy. Okay, so let's see. Let's go back here and see what we showed. We have shown that the Hamiltonian corresponds to the total energy as long as the generalized coordinates don't depend explicitly on time. If the generalized coordinates don't depend explicitly on time, and the Lagrangian itself doesn't depend explicitly on time, under those circumstances, the time derivative of the Hamiltonian is 0. The Lagrangian does not depend explicitly on time for an isolated system because the laws of physics are time invariant. So we can trace everything back to that. If the laws of physics are time invariant, then the Hamiltonian has the meaning of energy, and it is constant over time. In other words, time invariance of the laws of physics leads us to energy conservation. So we have now proven the second conservation law. So we have time invariance gives us energy conservation. We have that space invariance gives us momentum conservation. And there's one more conservation law that we haven't proven yet, and it's this one. Direction invariance. That is the notion that the laws of physics doesn't depend on the direction you face. That gives us angular momentum conservation. I'm not going to show that one here, but I'll leave it to homework. Okay, so these are this is pretty profound, right? Because we have these conservation laws, which are quite fundamental to what we're doing, and they come about just because the universe, the laws of physics that rule the universe, don't change over time, and they're the same everywhere, or the same in whatever direction you might face. These are aspects of what's known as Noether's theorem. It's due to Emmy Noether, probably one of the foremost mathematicians and physicists of the 20th century. And it states that, well, formally it states that any differentiable symmetry of the action of a physical system corresponds to a conserved quantity. You don't have to worry too much about the exact meaning of that, but the consequence, three of the consequences of that statement are these. There are others. For instance, conservation of charge, which we see in electromagnetism, is due to something known as gauge invariance. That's a more abstract notion having to do with the structure of electromagnetic theory. But Noether's theorem is one of the deepest and most profound statements in modern physics, and here we see some of the consequences of that.